Chapter 5, the standard deviation as a ruler and the normal model. So our objective is to express a distance from the mean in a standardized format. And this standardized format is known as a z-score. And the way that you reach your z-score is you subtract the mean from your data value and then you divide by the standard deviation. So z-scores measure the distance of a value from the mean in standard deviations. So for example, a z-score equal to 2 represents a data value that's 2 standard deviations above the mean. For a z-score of negative 1.5, that represents a data value that is 1.5 standard deviations below the mean. Now, whether your z-score is positive or negative, the farther the data value is from the mean, the more extraordinary it is. So two things happen when the data is standardized into a z-score. The first thing is there's a shift. So the data is shifted when subtracting the mean. The second thing that happens is the data is then rescaled when dividing by the standard deviation. So here's an example of what happens when we shift the data. So when we add or subtract a constant to each value, all the measures of position will just increase or decrease by that same constant. So if we look at this first data set here, 23, 56, 93, and so forth, all I did is I took every value in that data set and subtracted 25. So that gives me my negative 2, 31, 68, and so forth. It's just all of the values minus 25. Now let's look at our 5-number summary. On the left is the 5-number summary from our original data set, and then on the right is the 5-number summary from the data set after I subtracted 25. All of those values just shifted to the left by 25. Okay, so let's look at the mean. The mean from my original data set was 60.4. The mean from my original minus the 25 data set is 35.4, right? It's just, we shifted it. We subtracted 25 from it. So all of those values just represent that shift of 25 units to the left. Let's look at the range, the standard deviation, and the IQR. None of those values were affected by that shift. The range is still the range, standard deviation is still the same, and the IQR is still the same. So all we've done is we haven't changed the shape of the distribution. All we've done is we've just shifted everything 25 units to the left in this case. And this will work for whatever number you pick, whether you subtract or you add. So take a look at this data set and pick a number, and you can add or subtract, and add or subtract that number to your original data set, and then do the 5-number summary, and you're going to see the similar result as I'm showing you here. Okay, now let's look at rescaling. So when all of my data values are multiplied or divided by any constant, all my measures of position and my measures of spread are multiplied or divided by that same constant. So let's look at our same original data set, the 23, 56, 93, and so forth. I took all of those values and divided them by 2. Okay, so I took each value and just cut it in half. Let's look at our 5-number summary. If you look at the original column versus the original divided by 2 column, you can see in my 5-number summary, each one of those values was cut in half. 3 went to 1.5, 37 went to 18.5, and so forth. Now let's look at the mean. The mean also got cut in half, 60.4 to 30.2. Now here's the interesting part. Remember when we shifted, our spread was not impacted. Look at our spread now. We have a range. It was 90. It's now 45. Our standard deviation, 30.13. It's now 15.06. My IQR went from 51.5 to 25.75. So when we shifted, we didn't change any of our measurements of spread. Okay? When we rescale, everything gets impacted. Our actual data values, our summary statistics, and our measurements of spread. Now the data set has been rescaled. So let's go back to z-scores for a minute. So standardizing the data into z-scores is simply shifting them by the mean and rescaling them by the standard deviation. So by subtracting the mean from each data value, we shift the mean to 0, Okay, we saw this in the example. When we just did our shift, we didn't change the standard deviation, remember? Now, when we divide each shifted value by the standard deviation is also divided by itself, and the standard deviation becomes 1, right? Any value divided by itself equals 1, okay? How does the standardizing the data set affect the distribution? Well, the shape is not changed. We've shifted it, we've rescaled it, but the actual shape remains exactly the same as the original data set. We changed the center to 0 when we did our shift, and we changed the standard deviation to 1 when we did our rescaling. So what is a big z-score? Well, a z-score that's farther from 0 is more unusual and interesting. Okay, so there really is no universal standard, but just think that the farther away I am from 0, the more interesting that data point is. So remember with the IQR, we said 50% of our data lie between Q1 and Q3. Well, similarly, you can think of the z-score if you want to look at -1 and 1. Okay, it's not uncommon for roughly half of the data to be between those two points. And we'll get more specific as far as the standard normal, exactly how much data should lie between there. But roughly just think of it for right now as looking at your Q1 and your Q3. Okay, so the farther you get away from that, the more unusual your data set is, or excuse me, your data point is. So regardless of the shape of the distribution, a z-score that's more than 3 standard deviations is considered to be rare. And of course, if you have something that's a z-score of 4, 5, 6, 7, and so forth, that's going to be even more rare. Okay, so we're going to be talking about models, and more specifically, we're going to be talking about normal models. But a couple things I want to talk about models real quick is models do not match reality exactly. Okay, models are an approximation of reality. We can learn from them even though they don't match reality exactly, but they're close enough to reality that we can use them. Now the normal model, it's a bell-shaped curve, and it is appropriate for many distributions whose shapes are unimodal and roughly symmetric. And they don't have to be perfectly symmetric, just roughly or approximately symmetric. They provide us with a measure of how extreme a z-score is, and the notation is n, mu, and sigma. So this capital N, and then in parentheses you have mu and sigma, where the mu represents the mean and the sigma represents the standard deviation. Okay, the mu and the sigma are referred to as parameters of the model. So with our standard normal model, we have a mean of 0 and a standard deviation of 1. So remember, our standard normal model is after we did our shift and our rescaling, and our mean is 0 and our standard deviation is 1. Okay, so we have this normality assumption that we want to look at, because we can't use a normal model with just any data set. It has to meet this normality assumption. In order to check this normality assumption, we use what's called the nearly normal condition. Okay, so the shape of the data's distribution is unimodal and symmetric. And you can check this by making a histogram or a dot plot. Now it's better not to check this condition using a box plot, because the box plot will not show the shape of the distribution. So with a normal model, we have this 68, 95, 99.7 rule. So what that rule says is that in a normal model, approximately 68% of the data values are going to fall between -1 and 1. About 95% of the data values fall between -2 and 2. And about 99.7% of the data values fall between -3 and 3. So this is why we say if a data value has a z-score that is greater than 3 or less than -3, it's considered to be unusual, because based off of the normal model rules, 99.7% of your data should fall between -3 and 3. So you're going to have a very small percentage, if any, that fall outside of that boundary. So let's look at an example using our z-tables. So in this example, we say the math portion of the SAT has a distribution that is roughly unimodal and symmetric. The mean is 500 and the standard deviation is 100. So our first question here is, what is the z-score for a score of 680? Okay, so somebody scored 680 on the math portion of the SAT, and what we're doing here is we want to standardize that score. So what's the standard score that 680 applies to? So we have our formula here to get our z-score. So we take our data point of 680, minus off our mean of 500, and then divide that by the standard deviation of 100, and that gives us 1.8. So our z-score of 1.8 corresponds to a test score of 680. So that 680 has now been standardized. So now that we have our standardized score of 1.8, we want to find the percentile that's associated with that. Now the way we're going to do that is you're going to take your z-table, and the left column of the z-table is going to be the first two digits of your standardized score. So you want to follow that left column all the way down till you get to the 1.8. Now the row that's across the very top represents the third digit. So our third digit is 0. Okay, so we find 0 in our row across the top, and your percentile is going to be where those 2 points intersect. So from your 1.8, you move out to the right, your 0, move down, and you'll see that it intersects at 0.9641. Okay, now this means that 96.4% of the z-scores are less than 1.80. So in this example, we're going to work just the opposite direction as we did in the prior example. So in this example, we're going to be given the percentile, and we're going to find the z-score. So the question is, what z-score cuts off the top 2.5%? So what we're looking for is the z-score that has an area of 97.5% below it. So what you're going to do is you're going to go into the body of your table, and you're going to find 0.9750. Take your finger and move it to the left, and that's going to give you the first two digits of your z-score, which is a 1.9. Then take your other finger and move it all the way up to the top row, and that's going to give you your third digit of 0.06. Okay, so what that tells you is the z-score that cuts off the top 2.5% is 1.96.